Welcome to this lecture series in general topology. Last time we defined the notion of a topology and looked at various examples. And in this lecture, we'll discuss the notion of continuity. The reason why we study the subject of general topology is that we have a robust definition and robust machinery to work with the notion of continuity. So let's recall what we need. We'll need what is meant by a topology, of course. So a topology on a non-empty set X is a collection tau. In this slide, I have not written tau, I have written curly T, but I'll read it as tau. So it's a collection tau of subsets of X satisfying three axioms. The first is that the empty set as well as the full set is there in tau. The second is closure under finite intersections. So if you intersect two things in tau, you again get something in tau, which is same as saying that if you intersect any finitely many elements of tau, you again get something in tau, just a corollary of this thing by induction. And lastly, the union of any subcollection of elements in tau. So if these are elements of tau, or I should say that each u alpha is an element of tau, where J is some indexing set indexing these elements, then you take the union of all of them, you again get something in tau. Okay, so we discussed all of this at length the last time, and then we discussed some other phraseologies. So once you have a set X with a topology on it, then the elements of the topology are also referred to as open sets of X or open sets in X. That's also a phraseology that is used. So in the context of a given topology, we use the terms open sets to mean elements of the topology. Right? Every time we do not refer to the... In fact, the symbol for the topology is usually suppressed. We don't even mention it. We just say let X be a topological space, and it is understood that there is a fixed topology on it with respect to which we are working, and the elements of the topology are referred to as open sets. The complements of open sets are called closed sets, just a definition. And we also have the notion of neighborhoods. So if you have a topological space X, meaning a set X along with a topology on it, and you have a point little x in the set X, a neighborhood of X is just any open set containing X. And again, as we said, open sets just mean elements of the topology. So if you have a set capital X with some topology on it, and little x is an element of capital X, any element of the topology that contains X is called a neighborhood of X. Any open set containing X is called a neighborhood of X. In particular, the entire set X is also a neighborhood because the entire set X is in the topology. Okay. So a topological space, as we said, is a pair where the first thing is a non-empty set and the second thing is a topology on the set. And then we looked at a bunch of examples. You can read this list and try to recall the definition. If you feel you have forgotten one definition, then you can go back to the previous lecture. The most important example was the standard topology on R. I say important because the subject of topology is not motivated by these examples. It is motivated by examples of this nature. It is a great miracle, or it's a fortunate accident that the formalism for a topology captures some objects which we did not intend to capture. I mean, this is not something that we did not intend, but something like this and that, they are clearly, and even something like that, they were not in the purview of our imagination before these axioms, but these axioms do pull in such concepts and they are very useful. So yeah, so let's recall what is the standard topology on R. So a subset U of R, if you are given a subset U of R, will declare this open, or if that is confusing, we'll declare this good. So this is called good if you can write it as the union of open intervals. But put differently, we say U is good if for all X in U, there is some positive delta such that the delta neighborhood, or I don't know what to say, the interval of length 2 delta centered at X is contained in U. So this is the open interval centered at x of length 2 delta. This is contained in U. This is same as saying that U can be written as the union of some open intervals. That's exactly what it says. Okay? So if you collect all the good sets, including the empty set, so the empty set is good by convention. If you collect all the good sets, that forms a topology on R, and that is called the standard topology on R. Okay? And we will need the notion of convergence from real analysis. As I mentioned, real analysis is a hard prerequisite for this subject. So all the concepts, at least the main concepts from your real analysis are assumed. So recall that this is the definition of a convergent sequence. You can read it and you can pause the video and read it if you want. But you should be able to spell it in your dream. Okay, so let's proceed. Here are some problems for practice. And now let us get started. So we will define what is meant by continuity at a point. So we are given, or we have fixed two topological spaces. Again, for the last time, this just means that we have a set X along with a topology on it and a set Y along with a topology on it. We just suppress them from notation, and the way we refer to them is by using the language of open sets. So, when we say something is open in X, we just mean an element of the topology on X. And when we say something is open in Y, we just mean an element of the topology of Y. Okay? All right, so we want to define the notion of continuity. So fix a point X in X and let f be a function. Suppose we are given all of this. Then we say, and perhaps it's a good idea to maybe expand this a little bit. I mean, there was no need for this box, but I like to have this box around. So we say f is continuous at x if, so I'll write something down, but first let me explain via pictures. So we have this space x, we have the space y. This is typically how we imagine topological spaces. Here we have the point little x, and we have this function going from x to y. Okay? So f maps every point in capital X to some point in y. We are not insisting that this is a surjective or injective or any such function. It is just a function. Right, so we say this is continuous at the point little x if, what is the philosophy of continuity? It just means points which are sufficiently near to x map to points which are near to the image of x. That's the philosophy. So let's call, or let's not give it a separate name. Let's say the image of x is denoted like this. There is no let's say there. It is how it is denoted. So we'll choose a notion of nearness of fx. And then we want to say that once that notion of nearness is chosen, just like we choose an epsilon in the epsilon delta criterion, once a notion of nearness is chosen, there should be points which are near enough to x such that whenever you apply the function to them, you map inside this region which was a proxy for nearness. Right? So we'll just mimic that definition. And here nearness is not measured via some distance or some numbers. Nearness is measured by elements in the topology. Neighborhoods of the point fx are the things which are near fx. Once you fix a neighborhood of fx, that is a notion of nearness around fx. Just like once you fix an epsilon, that gives you a notion of nearness to a point on the real line. The points which are at distance less than epsilon, you can call them near y as measured by epsilon. Smaller epsilon has a more stringent notion of nearness, and so on. Anyway, so what are we saying? So whenever you choose a neighborhood capital V of fx, there should exist some neighborhood capital U of x such that all of U maps inside V. Whenever you choose points near fx, points which are sufficiently near to x, all of them map inside V. All points sufficiently near to x move near to fx. Right? That's exactly how we understand continuity when we study real analysis. All of this just abstracts this out. So let's write down the formal definition. So we say f is continuous at little x if for all neighborhoods V of fx, there exists a neighborhood U of x. So when I say neighborhood V of fx, it is understood that we are talking about this topological space. Fx is a point in Y, so a neighborhood V of fx just means an open set in Y containing fx. So this is just an element of the topology on Y which contains fx. Okay, so for all neighborhoods V of fx, there is a neighborhood U of x as shown such that the entirety of U goes inside V under the map F. Points which are sufficiently near to x map near to fx. This sufficient, the phrase or the clause of sufficiency comes because we have an existential or a existential condition, existential quantifier here. There is meaning sufficiently near. For all meaning just simply near. Okay, all of the philosophical underpinnings may not be immediately clear when you first encounter them, but at the very least the formalities should be clear and you should be getting some hint as to the naturalness of this definition. This is not just some arbitrary definition somebody pulled out of a hat. It's a very natural definition. Okay, but as with all abstract definitions in mathematics, one should understand them via examples, and one should have a good repertoire of examples at one's tips. So let's look at the most basic and the most useful and the most fundamental example, which is that of real numbers. And before I even go there, let me mention this gives the notion of continuity between any two topological spaces. You have a map between two topological spaces. As long as you choose a point in the domain, you can ask if the given map is continuous at it. Now, suppose we had a map from real numbers to real numbers, some map, and we think of the real numbers as topological spaces. Just equip them with the standard topology. So both copies of the real numbers are thought of as topological spaces under the standard topology. And suppose I have a point in the reals. Now, since we know real analysis, there is already a notion of continuity of the function f at the point x, the epsilon delta criterion namely. But we just learned another way to talk about continuity at a point with respect to the topologies on both sides. There is a topology here, there is a topology there, namely the standard topology. So this definition also furnishes the notion of continuity at the point x. So it is possible that these two notions of continuity are different. But if they were different, then we wouldn't be happy. The whole point of the subject is to generalize what we learn from real analysis, and if the standard topology doesn't work, then what will? The standard topology is, we saw that the open sets under the standard topology are precisely what we called open sets in real analysis, if you remember. Anyway, so the next thing is precisely establishing this equivalence. So suppose we have any map, suppose we have a map from reals to reals, and implicitly, whenever we have real numbers and we don't say anything, we implicitly assume that we are working with the standard topology. So in this slide, I will write it, but as we go along, we will forego such things. So here we have the standard topology. So think of both of them as topological spaces equipped with this standard topology. And we have a function from R to R, and x0 is a point in R. Let me call it x. X is a point in R. So think of this as the domain. So we have a point in the domain of F. Then the following two things are equivalent. Which two things? The first statement is that F is continuous at X according to the epsilon delta criterion. So this has no mention of any topology or anything. The epsilon delta criterion one can just write down. But the second one is F is continuous at X according to the previous definition. F is continuous with respect to the standard topology. So one should first of all appreciate that on the face of it, the two statements are different. There is a proof that has to be given. This was already given in real analysis. I hope you remember the definition. I mean, if you don't, then you don't satisfy the prerequisite. You should learn real analysis well first. And this we just defined in the previous slide. Okay, so let's try to establish the equivalence. So first, let's do 1 implies 2. So we'll assume that the epsilon delta condition has been satisfied, and we want to prove the second condition. So let V be, or let me call it W. Let W be a neighborhood of Fx. Okay, and it's good to draw a picture. So we'll think of the real numbers also as blobs, although that's a very strange way of thinking about real numbers, but it's fine. Right, so what we have done is we have just some neighborhood of Fx, we have called it V, W. Okay, maybe I'll make it a little bigger. All right, what do we want to do? We want to show that there is a neighborhood U of X such that Fu is contained in W. Now, there may already be a confusion here. When I use the word neighborhood, I don't mean to use it the way we use it in real analysis. I mean to use it the way we use it in topology, even though in this case they are the same. I mean, the whole point is that since we want to prove 2, we are using the word neighborhood as as in the context of topological spaces. So this is just an open set containing Fx, and when I say open set, I mean an element of the standard topology, right? Even in real analysis, we use this phrase, but I hope the distinction is clear. Even though they are the same concepts, the standard topology is precisely the collection of the same open sets as you have in real analysis. Anyway, I don't want to cause more confusion. So we want to show that there is a neighborhood U of X such that this happens, meaning we want to find some open set here such that the image of this lands inside W completely. Okay, but what does it mean to say that W is a neighborhood of Fx? It just means W is open under the standard topology, but what is the definition of the standard topology? By definition of the standard topology, we know, or we choose, epsilon greater than 0 such that this whole open interval is contained in W. Okay? Since W is an open set in the standard topology, such an epsilon must exist by definition of the standard topology. And we'll call this V. So this will be referred to as V. Let me draw it in the figure. So V is somewhere there. Okay. But by the epsilon delta criterion, we have assumed that one is true, and we want to prove 2. So the epsilon delta criterion holds is what we have assumed. So by the epsilon delta criterion, we know that there is a delta such that whenever we choose a point, it would have been better to call it x naught rather than x. Anyway, such that whenever a minus x is less than delta, we have fa minus fx is less than epsilon. Horrible choice of notation, but I hope you understand. Whenever we have a real number a which is less than delta distance from x, the image of a is less than epsilon distance from fx. Okay? Maybe it's better to call it x prime. That's a little bit better notation. Alright. So this can be written a little differently. This is same as saying, that is, the image of this entire interval is contained in this interval. Right? If you just try to unravel it, it's same as that. So just call this capital U, and this is anyway V. So we'll call that thing U. So it says that f of U is contained in V, but V is anyway contained in W. But U is an open interval and hence also open in the standard topology. Every open interval is open in the standard topology because the sets in the standard topology are precisely those sets which can be written as the union of open intervals. And of course, an open interval can be written as the union of open intervals. Just take that interval itself. Okay, so we have found such a U. We have found a neighborhood U of x such that this happens. Okay, so this proves 2. Right? And the proof of 2 implies 1 is very similar. This is an exercise. It's just the inversion of these steps, pretty much. Okay, so I hope you understood this proof. It's very important to understand this proof fully, as in appreciate every minor detail here. The proof is not at all hard. There is a notion of continuity that we learn in real analysis. There is a notion of continuity that we just defined. And when we use the word neighborhood here, we used it the way we defined for topological spaces. Even though a neighborhood of a point here under the standard topology is same as what we defined it to be in real analysis. If you take a real number A and ask for its neighborhood as we defined it in real analysis, it's exactly the same as asking for a neighborhood of A under the standard topology of R. So there is no difference, there is no clash, so to say, but in terms of proving this equivalence, here the word neighborhood referred to the way we use it in topology. Okay, there is a very subtle slight difference here, one should be able to appreciate it. Okay, and then the rest is just unraveling definitions. What is the meaning of an open set in the standard topology? We recalled it in the beginning of that lecture that around every point you should be able to find an open interval which is contained in the claimed set. In other words, we just use the fact that a subset U of R is open in the standard topology if for all x in U there is some delta greater than 0 such that, or maybe I'll say epsilon greater than 0 such that this epsilon neighborhood is contained in U. So that's the definition of the standard topology. And yeah, after that it's just a matter of definitions to prove this equivalence. And I have done one direction of it. The other direction is left as an exercise. Okay, so this is just maybe 1/3 of this lecture. We have a long way to go. So let's now proceed. Okay, so we look at another example via the notion of isolated points, which we will now define. Just give me a moment. Okay, so let X be a topological space and fix a point in it. Then we say that X is isolated in the space X, or in other words, or X is an isolated point in X. Many similar phraseology is used. So we say that X is isolated in X if the singleton is open in X. Again, just to remind, this just means that this guy is an element of the topology on X. So that's the notion of an isolated point. Pictorially, what you can do perhaps is you have this set X, and yeah, I don't know what else can you do. You can just kind of maybe, yeah, you can maybe depict the space like this. You can depict a point lonely and perhaps the rest of the space somewhere else. That might be one way to depict the isolatedness of a point, but I can't say anything better than that right now. Let's see an example, or at least two examples. So suppose we have a set with the discrete topology. This can also be sometimes more succinctly expressed by saying that let X be a discrete space. That's the same as saying let X have the discrete topology. So then every element of the space is isolated in it. Clearly, that's the definition of the discrete topology. In fact, discrete topology is precisely the topology in which every point is isolated. Okay, another somewhat more interesting example is you have this space. We discussed the topology on it. I'm not going to recall it. So the natural numbers in the space are all isolated. Every natural number is isolated in this space. But infinity, the symbol infinity, is not isolated here. So you should take that as an exercise to show that the singleton infinity is not isolated here. Okay. And for instance, another non-example would be you take the standard topology on the reals. No point is isolated. All right. Now here we have a lemma. So we have two topological spaces, X and Y, and we have a map from X to Y. Okay. So, sorry. Then you pick any point in the domain of F and assume it is isolated. All right. So let's be very clear about the hypothesis. We have a map between two topological spaces and we have a point which is isolated in the domain. Then the map is continuous at that point. So the upshot is, or another way to state this lemma is that any map between topological spaces is continuous at the isolated points. It may be continuous at other points also, but it is continuous at the isolated points by default. And the reason is extremely simple. This is not some theorem or anything. It's just an observation, so to say. But let me prove it in full detail. So let y equals fx and v be a neighborhood f little y in the target space. Always helps to draw a picture to understand things. Okay, that's the picture, and we have chosen a neighborhood of y, which I'm drawing in this color yellow. Okay. What do we need to show that f is continuous at x? We want to show that, or need to show that there exists a neighborhood, and let me use a short form, NHD. We'll use this to denote neighborhood U of x in the domain space, such that the image of U is contained in V. I've just enunciated the definition of continuity, but the end of the proof is just by observing you can take U as the singleton x. Since x is isolated, this is an open set. It of course contains x. It contains nothing else. In fact, it only contains x. So this is a neighborhood of the point x, and clearly the image of this whole thing is going inside the set V, because f of x is a point in the neighborhood V. So it's a trivial lemma, but it's important to enunciate it, at least the first time we are learning all these things. Okay, so that's it. That's the proof. Just this choice works. All right. Composition of continuous maps. Suppose we have three topological spaces, x, y, and z. Let me mark them out, x, y, and z. And we have a function from x to y, another function from y to z. Okay, that's the picture. Suppose we have a point in the domain of the first function, call it x naught, and nothing is written, and assume f is continuous at x naught. Also assume g is continuous at f of x naught. So f of x naught is here. Okay. So maybe it will help to color code a little bit. Let me give them some color, just to distinguish the maps from the points. Okay, so we have a function f from a topological space x to y, and we have a function g from the topological space y to space z. F is continuous at a point x naught, and g is continuous at the image of the point x naught under the function f. This maps to that under f. F is continuous here, g is continuous there. Then we can guess what is to follow. Then the composition g composed with f is continuous at x naught. This kind of thing we've seen in real analysis also, but here we have, since we have a very abstract setting, we'll need to reprove everything, or rather prove it in this full general setting. Composition of continuous functions is continuous. That's kind of the t-shirt version of it. Okay, so before we write down the formal proof, let us see the kind of the in words verbal explanation. We want to establish this composite function, this function. We want to establish this function is continuous here. How to do it? I mean, we just follow the definition. You first choose some neighborhood of this point. Some arbitrary neighborhood has been chosen. We want to establish the existence of a neighborhood of x naught such that the entirety of this neighborhood gets mapped inside this chosen neighborhood under the composite function. That's what we need to do. But this is the notion of nearness in Z. The continuity of g at the point fx naught furnishes us a neighborhood of fx naught in the space y, such that the entirety of this neighborhood is mapped inside this chosen neighborhood. Let's call it W. So the entirety of this, once again, so W has been chosen, some arbitrary neighborhood here has been chosen. Then you choose a neighborhood V here such that the entirety of V gets mapped inside W under the map G. Such a V exists because G is assumed to be continuous at the point fx0. And now, since f is continuous at x0 and fx0 is lying inside V, there is a neighborhood of x0, call it U, which maps inside V under the function f. And now it should be clear that if you take the image of U under the composite, you will land inside W because first you apply f, you land inside V, then you apply G, you land inside W, and that's it. We'll just write this down in words. You can skip it if you can write it by yourself, which I hope you can. So let W, here's the proof. Let W be a neighborhood of, let me use this symbol, choose some arbitrary neighborhood of this point. We want to show that or need to show that there exists a neighborhood U of x0 in X such that this containment holds. Okay. Now by continuity of G at this point, we know, or let me directly write, there exists a neighborhood V of y0 in Y such that G of V is contained in W. And by continuity of F at x0, there is a neighborhood U of x0 in X such that f of U is inside V. But if f of U is inside V, that implies G of f of U is inside G of V. All right. But G of V is inside W. This we know is inside W. And that's it. The above can be just used to deduce this. This is equal to that, and that is of course equal to that. That's it. Just a formal proof writing exercise. Okay. Now for something interesting. What about global continuity? What do we mean by that? So suppose we have two topological spaces X and Y, and f is a function from X to Y. We say f is continuous. Previously we defined the continuity of f at a point in X. Now we are saying f is continuous if f is continuous at every point in X. Right? So it's just a definition. We say f is a continuous function, period, if it is continuous everywhere. And most of the time, we will be dealing with continuous functions. The subject of general topology generally deals with continuous functions. We won't be interested too much in functions which are continuous at one point, but not at other points, and so on. But anyway, the definition of continuity, or global continuity as I would like to call it, has been given in terms of pointwise continuity. Just the condition that the function be continuous at every point is what is taken to be the definition of global continuity. Okay, and let's see some examples. Yeah, nothing has been written here. Just give me a second. All right, so here are a few examples. Let f be a constant function. What does that mean? It just means that there is some element of y such that f takes only that value. Right, I'm just elucidating what is meant by constant c. It's clear from the terminology, f is constant means it is not deviating, it is taking only one value. So then we claim that f is continuous everywhere. Constant functions are continuous everywhere. Why is that? Well, suppose we want to show continuity at a given point. So I just am trying to choose a color. Maybe I'll stick with white. So to see this, let x0 and x be arbitrary. Okay. And somebody has chosen some neighborhood of fx0. Right, again we can draw that picture. All right, so we have some neighborhood here and we want to find a neighborhood of x0 which maps inside this thing. But what is fx0? First of all, fx0 is nothing but this point y0. I mean, f takes only one value, so fx0 is the value that f takes, is the only value that f takes. Okay, so if you just choose this entirety of the set x as a neighborhood of x0, this entirety of the set x will map inside the neighborhood v. In fact, the entirety of the set x is mapping to this one point because f is a constant function. So that's it. You have found your neighborhood. Somebody chose this neighborhood of fx0. You wanted to find a neighborhood u of x0 such that the image of this neighborhood is inside v. But you can just choose the entirety of the set x and that's it. So I'll just write choose u equals x, if you understand what that means. So that proves that constant functions are continuous everywhere. Okay, second example. We have kind of seen this already. So let x and y be topological spaces. So since we don't have much space, we have let f be a function. From a discrete space x to a topological space y. Again, what do we mean a discrete space? It just means a set equipped with the discrete topology. It's a topological space where the topology is the discrete topology. So f is a function where this is a discrete space, then f is continuous. Then f is continuous because every point of the discrete space is isolated, and we have already seen that any function is continuous at any given isolated point. So the reason is just that every point of x is isolated. Okay, so if you have a discrete space, it admits every function as a continuous function, and this is the reason why discrete spaces are kind of boring. Okay, another very important fact is that let x be any topological space, then the identity function is continuous. What is the identity function? It takes little x to x, picks a point and just spits out the same point. So identity map is always continuous, and this is an exercise. Very, very simple exercise. Okay, another example of global continuity. Let f be a function from R to R, defined this way. So when we don't say anything and we use reals, then we are assuming that this is equipped with the standard topology. All right, so f is a function from R to R where R is equipped with the standard topology, and this is how f is defined. Then f is continuous. And why is that? Well, we've already seen that in the previous in a previous example, that the notion of the epsilon delta notion of continuity is exactly the same as the notion of continuity as we discussed for topological spaces. So everything that we learn in real analysis, the functions that we found were continuous in our study of real analysis are precisely the functions which are continuous in this new language. So this is just a special case. This is a polynomial function. We saw many other functions that were continuous, like the exponential function and so on. So all those functions we know are continuous. Exponential function and polynomial functions and trigonometric functions and so on. Everything, all of those are continuous. Okay. So this is just a measly shadow of that fact. All right. So let's proceed. So here is a very important theorem. The flavor of global continuity is somehow somewhat different from the local or the point-wise continuity. Even though the definition of global continuity is by insisting that the function be continuous at every point, it is really a point-wise definition. But somehow, global continuity takes a different flavor, at least in my mind. So what is this statement that I'm advertising? Fix any map between two topological spaces, X and Y. Then these two statements are equivalent. The first is that F is a continuous map, meaning it is continuous at every point of the domain. The second is pre-image of any open set in Y is open in X. Whenever V is an open set in Y and you take its pre-image, you get an open set in X. Somehow these two things are equivalent. And when I say somehow, I don't mean to insinuate that it's some difficult proof or anything. It's a very simple proof. But the shift in perspective, I believe, is significant. So why is this? So assume 1. Okay, we want to show 2. So let V be an open set in Y. Okay. Let's say we have the pre-image is F inverse V. I mean, there's no saying that it is F inverse V. The pre-image of V is F inverse V by notation. And we want to show that F inverse V is open. Okay. This stands for want to show that. All right. So now to show that F inverse V is open, pick a point in F inverse V. Pick some X arbitrarily here. Let X in F inverse V be arbitrary. Note that here is the key point to note. I mean, this is second nature once you study general topology in some capacity. So the key point is that we enough to show that, or we need to show that, enough to show that there is a neighborhood of X which is contained in F inverse V. So all I'm saying is this. You have a topological space X, you have some subset of it, call it S. Suppose you're able to show that for each point in S, you can find a neighborhood of that point which is also contained in S. So for each point in the set S, you can find a room around that point such that the entirety of that room is contained in S. Then the set S is an open set. The reason is very simple. You have the set S. For each point X, you have a neighborhood, call it UX. For each point X, you have a neighborhood UX which is contained in S. So if you take the union of all these UXs, you will get the set S, right? Because each UX is contained in S, so this union cannot be bigger than S. It has to be contained in S. But every point of the set S is present here because for each X in S, you have your UX which contains X. UX is after all a neighborhood of X, right? So this has to be the entirety of the set S. and that's it. So the set S has been expressed as the union of open sets, and any arbitrary union of open sets is open. So that's all I'm using. Maybe this should have been, this part or this piece should have been given as an exercise. Maybe it is given as an exercise, I didn't check. If it isn't, I will put it in the next lecture. So this one should realize that this is exactly, or this is the key point. This is what we need to show. Once we show this, we will have proven the second part. So how do we do this? Let's say y equals f of x. Then of course, y is in V. Why is that? Because you choose something in f inverse V and hit it by f, you will land inside V by definition of f inverse V. Okay, and now V is a neighborhood of y. So here we have your y. V now is a neighborhood of y. And y, remember, is f of x. So now, by the fact that f is continuous, we know in particular that f is continuous at x. Since f is continuous at x, and V is a neighborhood of f of x, by continuity, there is a neighborhood of x such that the entirety of this neighborhood maps inside V. So by continuity of f at x, there is a neighborhood u of x such that f of u is contained in V, right? V was a neighborhood of f of x, and therefore by continuity we have this. But what does this mean? This implies that u is also, or it's the same as saying that u is contained in f inverse V. So u is actually, will look like this. That's u. So we have accomplished this orange, or whatever this color is, that goal. We have found a neighborhood of x which is contained in the pre-image of V, and that's it. That proves that f inverse V is open because the point x was completely arbitrary. Around every arbitrary point, there is a neighborhood which is contained in f inverse V. Let me say that again. Around every arbitrary point in f inverse V, there is a neighborhood of it which is contained in f inverse V, and therefore f inverse V is open. So that proves 2. And for 2 implies 1, this is an exercise. This is easier. Will help you run the definitions in your mind once. Okay. So this has a simple corollary, which we could prove anyway without even the previous lemma. So let me state it and then say what I want to say. So we have 3 topological spaces, x, y, and z. And f is a function from x to y, g is a function from y to z. Always good to draw a picture. Alright. Assume f and g are continuous. Then the composition is also continuous. So we already know this. In fact, what we have shown earlier is that if f is continuous at a point and g is continuous at the image of that point, then the composite is continuous at that point. We saw this. So we can just use that. We want to show that the composition is continuous, which is to say that the composite is continuous at every point, but that is same as, I mean not the same as, but that follows because let's say x naught is your chosen point, then f is continuous at x naught because f is continuous everywhere. Oops. F is continuous at x naught, g is continuous at f of x naught, and therefore the composite is also continuous at x naught. So we see that this composite is continuous everywhere. But let us prove this using what we just learned. So we want to prove that this is continuous. So to do that, let W be an open set. W be an arbitrary open set in Z. What we want to do, or what we need to do, need to show that this is open in X. Right? But what is this? Simple set theory shows this is nothing but that thing. Let me draw a picture. So let's say we have W here. This is G inverse W. And then finally F inverse of G inverse W. Okay. So this is equal to that is a set theoretic fact. It says that first you pull back using G, then you pull back using F, or you directly pull back using the composite. Okay. So we want to show that this is open, but note that since G is continuous, the pullback of W under G is open in Y. Perhaps I should label the spaces. Yeah. So the pullback of W under G is open in Y simply because G is continuous and W is open. And the pullback of G inverse W under F is open in X because F is continuous. That's it. Therefore, this guy is open in X, and therefore this guy is open in X because these two things are equal. And this is a simple corollary of the previous thing. And yeah, so let's proceed. Okay, so now for an interesting example. So recall this space. What is the topology on it? First of all, what is that set? The set is the natural numbers along with a special symbol denoted as infinity. And what is the topology on it? The topology is first you collect all subsets of the naturals, and then you also put in such things. What things? Alright, and these will be referred to as tails. What is this? For each natural number, we define it as all those natural numbers which are at least n and infinity. So these will be called tails, or rather this will be called the tail starting at n. Right, and this was the topology that we discussed on this guy. So under that topology we are talking, we have a map from n infinity to n infinity such that it is a strictly increasing function on the naturals and it takes infinity to infinity. We want to show that it is continuous. And this is not the only hypothesis that leads to continuity of this function. Much weaker hypothesis will suffice, but for now this is good enough for us. Okay, and here is a small picture. Of course, this is a very strange way to depict that space, but that's fine. We are going to write it as if it were an abstract space. All right, so let's start with the proof. So first note that we just need to show the continuity of f at infinity. Why is that? Well, every element here, or rather let me be more precise. Every natural number is an isolated point in this space, and continuity of a function is for free at isolated points. Therefore, to establish the continuity of the function f, we just need to focus on infinity. Okay? So to do this, we will pick an arbitrary neighborhood of f infinity. So let V be a neighborhood of f of infinity, but f of infinity is infinity. F of infinity is infinity, but I'll just write it still as f of infinity, just for clarity's sake. Let me draw it in the picture. Alright, so we have chosen a neighborhood of f of infinity, and we want to show that there is a neighborhood u of infinity such that f of u maps inside V. Right, so this much should be clear. This is what we need to do. So since V is a neighborhood of infinity, by definition of the topology on our space, we can write V as A union Ln for some n. Right? All the neighborhoods of infinity are of this form. Okay, so not fix. I mean, V was some arbitrary neighborhood of infinity. It can be written that way. And now by the fact that f is a strictly increasing function on the naturals, so since we are given this, there is some symbol. Let's use a not such that whenever you have a natural number n, at least n naught, we have f of n is at least n. Okay, just immediately from our hypothesis. But then, therefore, since f infinity is infinity, we see f of Ln naught goes inside Ln, which is inside A union Ln, which is equal to V. Right? So f of L of n naught goes inside V, but L of n naught is a neighborhood of infinity. So just declare that as U. Call this U, and we are done. That's it. It was just a matter of unraveling definitions. In fact, most of the proofs that we will see most of the times in this lecture series will be about unraveling definitions, but there will be some actual interesting proofs and very powerful results. Okay. So now this is a separate lemma. This will not rely on the previous, what we just proved, but the topology on this space can be used to encode the notion of convergence. This is the point of this lemma. So fix any sequence in the real numbers and let A be some arbitrary real number. We can then define this function. This is just a function which maps the nth natural number to an, and it maps infinity to a. So infinity goes to a and the nth natural number goes to an. Now, what was the point, or what did we say was the point of this topological space? This was kind of saying that the natural numbers converge to infinity. So we would like to just kind of encode the notion of convergence, or we would hope that one can encode the notion of convergence using this topological space, and indeed we can. So the theorem is, then the sequence converges to the point A if and only if f is continuous. Okay? And let me record one side of this lemma separately. One can just say that if f is a function from n infinity to reals, then continuity of f implies that this happens. Right? That's just one side of the lemma. This side of the lemma. Continuity of f implies the convergence is what has been stated there. Okay, so let's now prove it. Again, it's just a matter of unraveling definitions, but it's just that since we need to do both sides, it will appear like a long proof, but the proof is not complicated. So first assume that the sequence converges to the point A, and we want to show that f is continuous. All right. And again, as we said in the previous proof, the continuity of f needs to be established only at the point infinity, because at other points it is for free. So I'm not writing that. So just need to show that f is continuous at infinity. So let u or v be a neighborhood. Yeah, v be a neighborhood of f infinity, which is a, right? Let me draw it. And here is an important remark. If you learned your real analysis well, you will follow this immediately. So may and will assume. Let me hold off this remark. Let me write one more line. What do we need to show? We need to show that. Want to show that, or enough to show that rather. Let me write that way. Enough to show that there is some natural number n such that f of ln maps inside V. Right, because what do we need to do? We need to find a neighborhood of infinity which goes inside V under the function f. And if we establish this blue thing, ln will serve as that neighborhood. So please realize that this is what we need to do. And now we may and will assume, we may and we will assume that V is an interval. Right, because since V is an open set containing A, it contains an interval containing A. So showing that there is some n such that f of ln is contained in that interval will be better than showing that it is contained under V, because the interval is contained in V. So we might just replace the set V with that interval and argue for that. Okay. Right. So that is where we are. But since we are assuming that the sequence converges to A, by definition of convergence, there is some n such that whenever little n is at least capital N, we have this distance is less than epsilon. Epsilon is a fixed positive number. So there has to be some capital N beyond which this happens. Okay? Which implies, which is same as saying that whenever we have that an lies in this interval, that is, whenever that happens, we have f of n is in V, right? This is same as f of n and that is same as V. So finally, this is same as saying ln goes inside V under the function f. Okay? So this is what we needed to do to prove that f is continuous at infinity, and this direction of the proof is now complete. So for the other direction, for the converse, assume f is continuous. We want to show that an converges to A. Okay. So to show convergence, what do? We choose an arbitrary epsilon. Okay, and write let V equals this guy. Again, one can use the picture from the previous page. Okay, so V is this interval, and we are given that f is continuous. So there is some, since f is continuous, it is in particular continuous at infinity. Therefore, there is a neighborhood O of infinity in this space such that f of this entire neighborhood goes inside V. Okay. But since O is a neighborhood of infinity, we know that there is some natural number such that this tail is contained in O, because neighborhoods of infinity contain tails. Therefore, this thing goes inside V. Since the image of this goes inside V, the image of that will also go inside V. And now if we just decode it, this just says, and this implies, which means this is the case, which means this is the case, and we are done, which is same as saying, since epsilon was arbitrary, we have shown that the sequence converges to A. It's just a reversal of the previous page. All right, so we have this. And now we can apply it to prove something we learned in real analysis in a very neat way. So suppose we have a convergent sequence in the real numbers and A be the limit of the sequence. Then we know from real analysis that every subsequence of it also converges to A. Every subsequence is convergent, and in fact, it also converges to A. So that is what we are going to prove using what we just learned. Then every subsequence of AN converges to A. Okay. So I encourage you to write your own proof for it. Whatever you learned in real analysis, you might want to repeat also. It's a good practice to recall or reprove things. That way they become solidified in our minds. But let me give you a proof using what we just learned. So to pick a subsequence, we will pick an increasing or strictly increasing sequence of naturals. So this be chosen. I'm not writing the full statement. What do we want to do? We want to show that this subsequence converges to A. Right? And recall by what we just did, if we define this function, define phi from n infinity to reals as phi of k equals A and k, and phi infinity as A, we just want to show that phi is continuous. Right? We just proved this. That convergence of this sequence to A is as good as continuity of this map. Which map? Which takes k to A and k and infinity to A. So this is what we want to do. And that we will do in a very soft manner. So first we have this function, the function f. What is f? F of n is an, and f infinity is A. Right? And we know that f is continuous. Why do we know this? Because of that and our previous proposition. Convergence and continuity of a certain map are the same things. So this convergence is same as continuity of this map. So we know f is continuous. And here we define another map. Which map? This map just takes, let us give it a name, maybe, let's say, I don't know, some nice name, maybe H. So what does this do? This takes k to nk and infinity to infinity. And we know H is continuous. We know H is continuous because of the previous proposition. That was precisely that proposition. If you have a strictly increasing function on the naturals, which takes infinity to infinity, that thing will be continuous. And lastly, what is this composite? We claim that this composite is phi, and this is not much of a claim because what is phi of k? Phi of k is just first you compute h of k and then apply f to that. H of k is nk and f of nk is ank. So phi of k is ank. I'm sorry, whatever, let me not call it phi as of now. So what does it take k to? K goes to ank. And what does infinity go to? Infinity goes to infinity and infinity goes to a. So infinity goes to a. And this is precisely the map phi. Okay, so phi is the composite of f and this guy, but this is continuous and that is continuous. So phi is the composite of two continuous functions and hence phi is continuous. And this is what we wanted to show to prove this statement. And we are done. So that's very nice. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.